This video lecture will finish up our discussion of standing waves in tubes, standing sound waves, resonances of sound in tubes, such as organ pipes, for example. Well, last time we discussed an open-closed tube. In that lecture, we discovered that the so-called fundamental frequency, sometimes just called the fundamental, was 100 hertz for a length of tube that's the same as the one we're going to study in this lecture. I show an open tube. The fewest number of letters, it satisfies the rules that are required for resonance, is 3. You must have an A at an opened end, and we have 2 open ends, so we have an A and an A. The other rule, not made clear or not discussed in the previous lecture, is that the letters have to alternate. You can't have 2 consecutive A's, 2 consecutive antinodes, 2 consecutive nodes. The same was true for string waves. So, to summarize, the rules that we follow for determining properties of sound wave resonances in tubes are these. You have an A, an antinode at an opened end, an N at a closed end, and the letters alternate. And for later use, we'll remind ourselves that the speed of sound is 340 meters per second. And there's the very important wave equation. The product of the wavelength and the frequency of any wave is the speed of the wave. In our case, it's 340 meters per second. The actual equation that we use is a variation of this one where we solve this equation for F. It's V, the speed, 340, divided by the wavelength. Let's use this equation to find the 2 lowest frequencies that will oscillate in a tube of this length, the same length as the tube we studied in a previous lecture. Well, we have the labeling ANA, that's 2 of these segments NAAN that have a length of 1/4 lambda. Let me record that fact here. We saw this last time. We'll use this all-important fact again. 2 of these distances are 2 quarter wavelength distances. This distance plus that distance must equal the length of the tube, 0.85. Solve this equation for lambda, and you see the result. I'll leave it in this form rather than report it as a decimal fraction. Use the equation shown here to find the frequency. It's the speed 340 divided by the lambda. 3.4 to 340 gives 100. Multiply the 2, that flips upstairs. Final result, 200 hertz. Now, you'll recall that the fundamental frequency, which we labeled F1 in the previous lecture, is 100 hertz. This is 200 hertz. It's twice the fundamental, so we have the right to label this frequency F2, where the subscript 2 reminds us that that frequency is 2 times the fundamental frequency. Again, the fundamental frequency for any tube is the lowest frequency that resonates in a tube that is open at one end and closed at the other end. Let's find the next lowest frequency that resonates in this open tube. Well, the next fewest letters that we can draw on this tube, A at each end, and the letters must alternate, AN, AN, A. There are 1, 2, 3, 4 of those distances, those important NA distances, each one being 1/4 lambda in width. Add them all up. 4 times 1/4 lambda must equal the length of the tube, which is still 0.85 meters. Solve this for lambda, and we have 0.85 meters. Finally, the frequency using this equation is the speed 340 over 0.85, 400 hertz. How shall we label this frequency, I think you know what's coming. Since this frequency is 4 times the fundamental frequency, which is symbolized F1, by rights, this frequency should be labeled F4. If I were to ask you to calculate the next lowest frequency, or the next 2 lowest frequencies that will resonate in this open tube, I think you could see the pattern looking ahead. If you go from 200 to 400, the next one will be 600, then 800, then 1,000, then 1,200.